We're going to continue our tour through the tidyverse by looking at the readr package. The readr package is all about getting data into R. In particular, readr contains functions to read in datasets and in many cases also write those datasets to disk. There are other similar packages that are related to readr that I'll talk about at the end of this. They're the readxl package, Haven, Vroom, and Janitor. They're all similar packages, but they're all special in particular ways. This slide deck contains information about how to import flat files that have data into R, generally speaking. There are some variations of that, but that's the general idea. Mostly I'll talk about reading in CSV files. That's probably the most common file format to get data, but by no means is it the only kind. In particular, in this slide deck, I won't talk about any web-related data files, so I won't talk about reading in HTML files or XML files. That will come in the next lecture, and I won't talk about reading in data from a database. That will also come in a future lecture. To begin, it helps to review what base R has for reading and writing CSV files. The base way to read and write CSVs is with those functions. So as an example, I can create a temporary file with a temp file function. This is also a base functionality and will be operating system dependent. So this is simply a file name. It looks like gibberish, but it's allotted by the operating system itself. I'll then create a tibble and then simply use the write.csv function to write that tibble to disk. Notice, by the way, that I need to write row.names equals false because it's defaulted to true. So if you ever read in a data set and the data set has an empty first column name, the first column will usually be populated with rows, so like 1, 2, 3, all the way down to the number of rows in the data set, but it'll be missing a name. The reason is that whoever created the file used write.csv, but they did not give it row.names equals false. So it wrote the names in, but it didn't put a name with that. If you use file.show, RStudio will show you what that file looks like, or if you use file.edit, it will show it in a text editor. This is a useful way to actually see your file. In many cases, and we'll go into this more in just a moment, but in many cases it's actually useful to actually look at your data if that's possible. For very, very large files, it may be prohibitive, but in general you can usually look at your data in a text editor, and that's a very useful thing to do for reasons we'll talk about in just a minute. When we want to read this in, base R provides read.csv. You give it the file name and it reads it in. The resulting object is a data frame. It'll say, 3 observations, 2 variables. Notice that it does things like this. It'll convert strings to factors. Over there on the left-hand side, we can see that originally y was defined as a character vector, but now it's a factor. R has strings as factors equals false by default. You can change that in the read.csv function, or data frame and other places as well, but this behavior is slated to go away in R version 4. So hopefully we won't have to deal with this for too much longer. Nevertheless, this is the R that we have right now. There are some differences provided by readr that base R doesn't have. And in general, these kind of follow the ethos of the tidyverse. First, there's consistent naming and specification. In particular, readr functions will always create tibbles. Or almost always. There are a few exceptions that are noteworthy, and it's very explicit that they're not going to be tibbles. Readr functions will also have names that have a conventional syntax using underscores instead of dots. So instead of read.csv, you'll get read_csv. And if you want to see all of the functions in the package that do that kind of thing, you can see them right here. So there's a ton of read and write functions for different file formats in readr. Nevertheless, read_csv is far and away the most important of these functions, so we'll talk about it a lot in this video. With read_csv, you usually have 3 kinds of specifications. Either you have a file that is directly from disk, meaning that you need to point to things correctly and so on. I say remember here, I mean the here package that provides for convenient pathing that is portable across operating systems as long as you're using an RStudio project, which is a really good idea. You can read directly from the internet if you put in a URL. This is a useful thing that you can do, and many tidyverse functions support it. So we'll talk about this more in the next lecture. Or lastly, you can actually read directly from a character vector. This is something that is actually unique to read_csv as distinct from read.csv, and is really helpful for understanding simple examples of how read_csv will parse things, so that you don't have to actually create an actual file and then try to import it. You can actually have those two things kind of in the same spot. So you can tinker around with the stuff inside the character string and see how read_csv will parse it, as opposed to having to manipulate the file. Of course, as a basic level of functionality, you can do things like this. Read_csv doesn't really care about white space, so it'll parse things nicely into tibbles, which is exactly what you would expect. Now, read_CSV also deals nicely with the tops of files. For example, it's common to have data sets in CSV files that actually have some header information in the top that usually explains something about variables. Okay, so in this case, it says this file contains data from Dr. Harville's class. And when you try to read it in, it'll give you these warnings, these parsing warnings. We're going to see these throughout this video. And it'll return a tibble, but the tibble is totally different from the tibble that you would want. The problem here is those first two rows. This file contains data from Dr. Harville's class. Those are not actually data, and whoever created the file did not intend for them to be just like read in just directly. You can get around this with read_CSV by using the skip argument. The skip argument will tell you a number of lines to skip at the beginning of the text file. Okay. Now, then the question would be, how do you know how many lines do you actually skip? And to do that, that's where you're going to use something like file.edit, or you'll open up the data set in Excel or something like that to actually just look at the data. Okay, remember, that's a very important thing to do. And when you do this, of course, it reads it improperly. Another convention that you'll see commonly is people will use some kind of demarcator at the beginning of the file to communicate to the user, this is not a row that is actually meant to be read by whatever your engine is. Okay, so they're comments of a particular type, but this is not comments in the terms of a programming language. This is actually comments in the data itself. So there's just a convention in the file to do that, okay? Of course, if you try to read it in, you get disaster. You can create this with comment in read_CSV. You can specify what the commenting character or characters are, and then read_CSV will not read those lines and will read the others, okay? Column names, by default, read_CSV will expect the column names to be present, okay? If they're not, you'll get a situation like this. Read_CSV, and they come straight at you with the data, okay? 1, 2, 3. It will actually take whatever that first line is, and those will be column names, even if you may not think that those are valid names in the R language. Remember that we call those non-syntactic names, and you'll know them by their demarcators, which are those backticks, okay? So whenever you see backticks around like a name or something like that in the R language, it means it's non-syntactic, and it's actually a variable name. If you want to specify that no column names come with that particular file, you just say call names equals false, okay? And then it will actually create names for you. So here, x1 through x3, or however many columns that you have. You can also define names at readin, and you should only use these when the column names are not actually present. Okay, so you would not use this to like overwrite column names that are there. We have different ways to deal with that, and we'll see that later. Okay, so to do this, you'll use the call_names argument again, but this time you give it a character vector. Okay. Now, onto column types. CSV files are actually strings, and so their entities, their individual elements, are unknown typed observations, right? When R is reading in this data, it doesn't know that column 2 has strings in it, or that it has factors in it, or something like that. However, read_CSV in general is good at guessing types, but best practice will be to actually specify how to parse the types manually, okay? For example, let's say that your file looks like this. It clearly has 3 columns. Those are date, X, and Y. The date column is clearly a date in time, so it should kind of be converted to a date object in the R language. And the last one is a string, or maybe it's actually a factor. It's not entirely clear from looking at the data set, and you would need to know from whoever created the data set, okay? When you read this in with read_CSV, it's actually smart enough to know that the first thing is, in fact, a date object. So it has some kind of smarts built into it to parse just basic objects from character strings to detect that that's what that thing is, okay? Which is a really nice feature. If you're just kind of reading in data, that's a really nice thing to do. I'll talk in just a minute about when you want to be more careful about data types and so on, how you can deal with those. But at this point, that is a really nice feature of read_CSV, that it'll automatically detect those types. If you want to specify them directly, the most succinct way to do that is using the call types argument to read_CSV, and you will specify a character string, and that character string tells you what kinds of objects you want each of those columns to be parsed into, okay? So the first one is a date, and that's signified by the capital D. The second one is an integer, that's an I, and the third one is a character, that is a C, okay? Notice, by the way, that that integer is not what it would have guessed, okay? By default, it actually guesses numbers as doubles, okay, which is probably not surprising coming from base R understanding, but that's how these things will usually work. So again, you get shorthand codes for column types, and the codes look like this, okay? L is logical, I is integer, D is double, N is number or numeric, C is character, F is factor. There's going to be some issue there with the levels. D, capital D is date, capital T is time, question mark is guess, and dash is skip, okay? Now, in this case, we actually illustrate some of those. So here we have call types is question mark dash C, okay? Again, the dash is used when you actually don't want to read in the column at all. So question mark says, hey, I want you to try to figure this out, reader. Dash says skip, and C says it's a character, okay? And that's why we're missing that X column right there in the middle because we dashed it out. Now, if we want to have longer specifications, it's possible to put in longer specifications, and there's reason why we may want to do that. We do that with the calls function followed by a number of call specifications, okay? Here's an example. I'll use read_csv, the same file, but now I give a significantly longer syntax of the column types. Why did I do that? Well, in this case, it's not actually necessary. We know that in general, those things were read correctly, but if we have a date that has a particular format to it, okay? In this case, that says year in the sense of a 4-character year, like 2020, dash month, which is the numeric 0, 1, 0, 2 up through 1, 2, and then day, of course, 0, 1 through 31, okay? However, look here, with call factor, that's something that we actually did not have before. We didn't know that that column was a factor column. And so if we want to say, hey, this variable is actually a categorical variable and it has an order to it, this is the way that we need to do this, okay? We need to say parse y as a factor and it's ordered, okay? So ordered equals true, and that's in the call factor specification, which is in calls. So clearly, this is a significantly more verbose way of reading something in. But in many cases, when you need to do something really correctly and it's important that everything is read in properly, this is how you want to do your specifications. Now, you actually don't need to quote these names on the left. I usually do that when I'm creating tables or lists, but it's actually more common practice in R not to do that. So just know that that's around. Now, you can also read in select columns with call types, and this is the way that you do that. You use the calls only function instead of the calls function, and then you just specify the names of the columns that you want. Read_CSV also has some support for NAs. So if there are NAs in your data set and you know how they're coded in advance, you can deal with them that way. Here's an example where there are 2 NAs in the data set and they come kind of in the way that you would normally see them in R. So they're just capital N, capital A, capital N, capital A in 2 different places, okay? When you read those in, read_CSV is smart enough to know, okay, those are missing values and I'm going to code them like that, okay? It's common, however, in other circumstances to get things like -99. And when they do that, you can specify this in the read_CSV function as NA equals, and then you give it a character string that contains whatever the coding is for a missing value, and it will actually parse that correctly. So you can fix NAs all over your data set immediately using this scheme. You just have to know how they're coded. Next, we'll talk about type parsers in readr. Remember, parsing is that idea of converting one type to another, and in CSVs, they're all characters. So you're always converting characters to other types, okay? Reader's parse functions are very much like base's as dot functions. So, parse underscore number is like as dot numeric, roughly speaking, okay? If we wanted to look at kind of the table of all of them, this is an augmented table from the one that we saw before, and it has all of the functions you may be interested in. Each of these parsing functions has something a little unique to it, so it'll help us to go through each of these individually. First, parse logical. Parse logical at a base level works exactly how you think it's going to work, okay? Trues, falses get parsed as trues as falses. T's, F's get parsed correctly. Zeros and ones, if it's 1, it's true. If it's 0, of course, it's false. But if you try to do something else, like not 0 and 0, that's when you're going to run into issues, okay? So you get this warning, 2 parsing failures because you're trying to pass in a 0.5 and a -1. It tells you what it expected to get here. So it expected to get one of these, 1, 0, TF, true or false, and it actually got those, okay? This is a really nice feature of reader functions, and the parsing functions in particular, is that they'll tell you what they were expecting and what they got, and kind of where the problems are. We'll come back to this at greater detail in just a little bit, but that's a really nice feature of most parsing functions in reader. Notice also that in that case, only the offending values were converted to NAs. So if we look to the original vector, this was bad, this was good, and this was bad. Well, this is bad, this is good, this is bad. Okay, so it will correctly parse the ones that should be correctly parsed, and the one that it's not sure about, it'll warn you about them, and then you'll get them as missing values. Notice also that it has this problems attribute at the end. This problems attribute is actually going to contain all of that warning information, and we'll see a way later that we can actually extract that. Parse integer and parse double, both of these also work pretty much exactly as you would expect. There are a few little issues with them. So for example, parse integer works fine with just encoded integers. And in fact, of course, you can check that they are actually parsed as integers. Strangely, it actually doesn't work with scientific notation. And this is true, although it's not on the slide, it's true even if you have scientific notation that has the L's on the end, which actually specifies them in base R as integer literals. So this would be expected to actually not work, but if they had L's on them, that also does not work. If you use parse integer with decimals in them, of course, you expect to get problems. You do get problems, and those are parsed as missing values. By contrast, if you use parse double, they parse exactly as you think, whether it's just obvious numeric representations or if you're using scientific notation. Now, here's something a little bit different, and this is again something that you would not necessarily expect. If you're parsing data from sources that are just different than what you expect, strange things can happen. For example, for numbers, it's common in Europe, for example, to instead of using the period for the decimal mark, to use the comma for decimal marks. So if you have a data set that has commas in for periods, you need to have some kind of parsing function that can support that kind of thing. And that's precisely what the parse double function will provide you with, and it does it by this locale argument, okay? So each of these functions will have a locale argument, which generally speaks to something like where are you in the world, or a specific aspect of the locale, which is what decimal mark is used, what grouping mark is used, things like that. So this is one of the nice features of a number parser that you may not actually expect when you're trying to read in data. So in general, locales will allow for parsing of kind of colloquial formats, be they numbers or be they characters or something else. readr also provides a function called parse number, which is like parse double in the sense that it's going to parse things into a numeric or a double object, but it also allows for symbols either before or after the encoded number. For example, in many cases, you'll see things like currency notation, so dollars, euros, pounds, Bitcoin, whatever, either before or after, and it will be able to parse those exactly as you think, okay? Many numbers of practical interest are encoded that have percentage signs after them, so those will be parsed by parse number, or in a situation like this, parse number will work here as well, where you have a phone number, and the phone number has grouping marks that are dots. We know that we could actually use string processing to parse a lot of this, but in some ways that's the features that stringer functions are providing for you. A lot of string processing that is kind of pre-prepared for you and ready to go. While on the topic of numbers in R, and as a kind of segue into characters in R, it helps to talk about some kinds of encodings of numbers in R. Not necessarily how they're represented under the hood, but how you can refer to those numbers, okay? In particular, you can actually refer to hexadecimal numbers directly in R. So hexadecimal numbers, remember, these are just numbers that are represented as hexadecimal digits. And to do that, we use the symbols 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A, B, C, D, E, F. So those are the unique symbols that will refer to the numbers in decimal that we call either 0 to 15 or 1 to 16, depending on how you want to look at it. Okay, the binary representation of those is going to require 4 binary bits. And those binary bits, 2 to the 4th, will give us the 16 combinations that we need to refer to one hexadecimal digit. Of course, a common jargon here is 1 byte. 1 byte is equal to 8 bits, which is 2 hexadecimal digits, which can hold up to 256 different combinations of things. So whenever you see 1 byte, it's representing up to 256 different things, okay? 2 hexadecimal digits. Now you can refer to these directly in base R using the 0x followed by whatever the hexadecimal digits are. So for example, the hexadecimal number 1f is referring to 1 times 16 to the 1 plus f, i.e. 15 times 16 to the 0, and of course that is 31, okay? So when you type in those numbers, it's actually automatically going to convert them into decimal for you. If that specification is in a character string, as.numeric will support that just fine, okay? You can also do the inverse conversion if you type in as.hex mode. You can give it a decimal digit and it will convert it into its hexadecimal representation, okay? So you may think, okay, well, as.numeric works like this, parse number should work like this. And unfortunately, actually, parse number doesn't work like this, okay? Not only does it not work like this, it gives you the wrong result because it expects something different, right? Parse number is looking for kind of the first number that it sees. It may be preceded by symbols, it may be followed by symbols, but it's going to pull out whatever that first number is as a double, okay? Parse double also does not work. This will give you actually a different specification though. It will give you NA followed by problems because it doesn't expect any symbols at all other than scientific notation type symbols. It's worth noting that in many other languages you can also specify numbers in binary explicitly. To do that, you usually do something like this, 0B followed by the digits that you want in binary. Okay, this actually does not work in the R language, but it does work in a language like C++, and you can evaluate that using the RCPP package using eval CPP. So you just tell it 0B1001, and we know just from our table there on the right that that's the number 11 in decimal. I bring this up to talk about character encodings. It's useful to talk about character encodings because they come up all the time in non-Latin text, okay? Characters are encoded at a lower level as simply a sequence of bits. So there always has to be a code that converts sequences of bits into a character. There has to be an association there, okay? The classic encoding between bits and characters is referred to as ASCII. That's the ASCII, and it stands for American Standard Code for Information Interchange, okay? It's an old system that's set up. It has 7-bit sequences, so there are 2 to the 7 or 128 possibilities. And that has to encode everything like all the letters, capital, lowercase, all the numbers, punctuation, and so on. Many of these characters are actually non-printable, okay? Meaning they're tabs or spaces, a backspace, and other kinds of things we'll see in just a moment, okay? But many of these encoded possibilities, of the 128, many of those are not things that you see. However, it does encode all Latin characters, so for a long time this was kind of all we needed, was just something like this to get by, because we could just type in all of the basic text that we need, and for English speakers this was generally a satisfactory solution. Now the code itself is communicated in what's called an ASCII table. And the ASCII table has several columns here. You can see that there's the decimal column here on the left, hexadecimal, binary, octal, which is the base 8 system, and then the character that they actually represent. Okay, so many of these, like all of the first ones, for example, all of those, so the first, let's say 32 and decimal, are all things that you don't actually see. Okay, the first thing that you see is 33, and that is the bang. Numbers actually start at 48 up here. That's where you get 0. And then letters start here at 65, and they go all the way down to 90. And then there's kind of a break before they pick back up again in the lower case. So there's a lot going on with this ASCII table, but the ASCII table is just generally a way to encode Latin characters and numbers and so on into bit representations. And it was standard for a very long time. Nowadays, ASCII is extended by many encodings because we want to have more than 128 base possibilities, okay? The most important extension to these encodings is referred to as Unicode, and the way that you actually see it in practice is UTF-8, or in far less circumstances, UTF-16 or UTF-32, okay? UTF-8 is a variable length encoding and can support up to 4 bytes or 8 hexadecimal digits of different possibilities for the characters. So UTF-8 supports a tremendous number of base characters, far, far, far more than we would need for English for sure, but other languages as well, and we'll see this in just a moment. To see this, let's actually highlight in on a particular part of the ASCII table, which is this K right here. This will help us to understand how this works in R. In particular, note that K in decimal is 75, and in hexadecimal is 4B. And of course, that's the capital K that we're referring to. The lowercase k will be a little bit different. Base R has the function UTF-8 to int, where you give it a character and it gives you back the number in decimal representation as an integer. If we wanted to convert this to hexadecimal, of course we would use as.hex mode, and here it's 4b, which is exactly what we saw. You could have done this originally by using the char to raw function, and you could do that directly. You get the 4b there. That is actually a raw data type in R, and that is, of course, the kind of most crude data type that R has. It is an atomic type. Now, you can actually refer to these in character strings, and you will see this fairly frequently with special encodings. The most basic one is /x, and it's fairly rare to actually see this, but it does come up sometime. So /x followed by the hex representation of whatever the character is will give you that character back. /x4b is the letter K. A more common way to see this in R and in textual data is /u. So /u will allow you to specify in a basic way the Unicode representation of that particular character. So here it's 004b, that is 2 bytes represented in hexadecimal, which is 4 digits. Of course, K is a Latin character, and the whole reason why we're doing this is to go beyond Latin characters, right? So let's take something that's not Latin, like the delta, okay? Delta in integer would be 948. Obviously, that's not supported in ASCII. If you use hex mode, it's 3b4. You can use the /u notation, /u3b4, and we get delta back. Or we can even go further into things that are not even characters, but in the computer, or to the computer, they are characters. In particular, things like emoji that you get all the time in text data these days that before you never really would have thought about these things. So UTF-8 to int, this is 9,996. Its Unicode representation looks like this, and we could have obtained that using as hex mode UTF-8 to int, okay? Now, this doesn't always work as nicely as you might suspect. For example, if I use this emoji's int looks like that. The hex mode is this, but if you actually just try to use the /u, that doesn't work, okay? It gives you 2 characters back, okay? And the reason why is that /u only allows the specification of 2 bytes or 4 hexadecimal digits. So what we're seeing here is /u 1f60, that's 1 character, that's the omega with the accent above it, and then the 2 coming at the end, okay? By contrast, if you use /U, you can specify a larger bit of the Unicode sequence, and then we get back exactly the thing that we're looking for. But we do have to use cat on it to see what its printable form is, okay? So it's kind of odd, but these are the kinds of things that come up when you're actually dealing with textual data. Luckily for us, parse character knows all about these things. So at a basic level, parse character is going to work on the Latin text in exactly the way you expect, okay? ABC comes ABC, okay? Alpha, beta, gamma gives alpha, beta, gamma, and those are going to be Unicode encoded. If you have other kinds of textual data, emoji or Unicode specified things, those are also able to be parsed by parse character, and even when they're mixed around. Now, the actual encoding of the textual data can matter in circumstances. If you don't know it, you can use readr's function guess encoding to actually guess what that encoding, what that textual encoding is. There are low-level libraries to try to do this, and it's not perfect, and that's why you see that there's a confidence associated with the guess there, but it is fairly reliable. In general, readr functions are going to assume UTF-8 encodings, and this can be specified manually with locales. So if you're dealing with a lot of textual data that is not in English, you may want to actually start looking into locale-dependent textual encodings. Now, if you don't know what the parser should be for a particular character vector, you can use guess parser. Guess parser is going to communicate back a character string specifying which parser it should use. And then if you use parse guess, it's actually going to apply that parser, okay? This is actually what is being used in readr functions. And what readr is going to do is it's going to use parse guess on the first 1,000 observations of each column, as long as it has 1,000 observations. So it's going to use that guessed parser to figure out what it is, it's going to apply it with parse guessed, and that's how it's actually going to do those question mark column types that we referred to earlier. And in general, things work very well as you would expect. Again, best practice is going to be to actually tell it specifically which parser to use, but that's how the guessed parser is going to work. Now, when problems do arise, we've seen them before, they arise as warnings, and then they arise as attributes, okay? So you'll get something back like this. Here I say parse number, and then I give it characters as well. It tells it what was expected, and it tells it what the actual user gave it, okay? Notice, though, that the bottom has that attribute of problems. If we use the problems function on the result of something that's parsed, we get that thing back as a tibble. That can be really useful for actually identifying which parts of our data are not being parsed properly. And maybe I'm going to go back into my text editor or go back into Excel, and I'm going to look at those rows and those columns to isolate visually what's going on and why is this thing not reading incorrectly. So individual parsers can create problems, okay? But the read functions, as we know, can create problems as well. For example, if I say read_CSV and notice that that last row has the 7 at the end, it tells us that there was kind of a column mismatch problem. And this is very common when you're reading in data sets, that something like this happens. There's an incomplete row, or there's a row that has too many observations in it, or something like that. Read_CSV is very good about those things. We'll warn you about them, and then you can pull them back with problems. Next, we'll talk about reading and writing specific objects onto disk, okay? So base R has these two functions on the right, read and save RDS in capital letters. The tidyverse version of these in readr is just read and write _RDS, and it's a very thin wrapper of the base versions, which are already very good. So the idea is to take an R object, it may be a data set, but it may not be a data set. It may be a function or something like that. And you want to write that to disk, okay? So that when the user reads it back in, it's going to still have all of the encodings and all the R trappings that you would expect. For example, if you wrote something into a CSV file and you read it back in, it's going to lose all of its factor status because CSVs can't support the idea of factors. But R objects, of course, can. So if you write them as RDS files and you read them back in, you're going to get exactly the same file as when you wrote it out, okay? So this will read in reliably as the object that you are writing to disk, okay? You can be sure that when you pull it back, this is what you're going to get. And in general, this is a good way for us to store data in a long-term format or to give it off to other people. I'll note in passing that when you actually use it, and we'll see this in a minute, it's imported and it's stored. It's not like save or load. Here's an example. If I say list.files, there's only one R script file in my directory right now. I can create an object called A, and I'll save A as the file name a.rds, okay? I'll list the files, and you see the file there. Then I'll remove A, so the binding is gone from R, and the garbage collector is going to come and remove it from memory. So A is no longer there. Then I'll assign that same object to something called B using readrds. So readrds is going to pull it in. Now I need to actually store it somewhere. I'll store it as B, and B has the value of 5, which A did at the beginning, okay? Of course, A is still gone. So it doesn't create the binding back in our environment called A. That thing is totally gone. And then, of course, I can remove a.rds with file.removed to kind of clean up after myself, and I can check that it's gone with list.files. Lastly, there are a few packages that we want to talk about that are related to readr. The first one is vroom. Vroom is very, very much like readr. The difference is that it's more limited in scope, and it's really for reading in CSV files very, very quickly. Okay, the specification is almost the same as read_CSV, but it's going to be probably orders of magnitude faster. It's also a little newer than read_CSV, so if you don't need all of the speed from vroom, just go ahead and use read_CSV. But if you have something that's larger or you're reading in a lot of things, consider vroom. Next, there's the skimmer package. The skimmer package is useful for skimming a data set once you've read it in. So we've seen in Tibble that there's the function called glimpse, and glimpse is kind of like a beefed up version of str, okay? When I use it on the iris data set, of course, has 5 different variables, and you can see them right there. But it only shows you what the data looks like kind of at a surface level. If you use skimmer, you can see a lot more about that data set, okay? So you can see things like how many observations are there, how many columns. So that's not too surprising. We had that information before. How many factor variables are there? How many numeric ones are there? Are there any grouped variables? So we'll see this in dplyr. Then it breaks up the skimming by the variable type. So here we have factors, and down here we have numeric values, okay? And it will say things like, well, of the species variable, were there any missing values there? Or of these others, were there any missing there? What proportion of them were actually all there? For the factors, is it an ordered factor, is it not? And then, of course, for numeric data, we get things like basic little histograms. And all of this is actually showing in the console window itself. Next, we have janitor. Janitor is a very, very useful package that has effectively one purpose. It does a few other things, but its major purpose is just to clean names, okay? So let's go back to that iris dataset for a moment. We'll see that iris dataset has variable names like sepal.length with capital S and capital L. and it has that period in it. So obviously these are the kinds of names that we would want to change to kind of convert it into a more tidy format. And that's exactly what janitor gives us. The most important function in janitor is undoubtedly clean names. You pipe a dataset directly into clean names and it will try to clean the names for you. Now, clearly there's just a bunch of string processing that's going on to kind of tidy up these names, but it's very flexible and it's very useful for this particular purpose. We can change the convention of the cleaned names if we like different conventions. For example, if we want the names in lower camel case, we can just specify that, and it will put all the names in lower camel case. It won't have the underscores, or upper camel, or so on. There's the whole gamut of things that you might suspect. There's also screaming snake case, which is common for dealing with databases, which is all caps with delimited by underscores. So there's a lot of flexibility here in cleaning names. And of course, it doesn't just clean things like periods and uppercase things. It will also change in general non-syntactic names into syntactic ones that are useful. So for example, if the name looks like a function call, it'll have open and close parentheses. It will throw away the close parentheses and it'll change the open parentheses to an underscore or something like this. The last thing that we'll talk about are the readxl and Haven packages. readxl is used for importing Excel spreadsheets. So if somebody gives you data and it's in an Excel spreadsheet, that's a very common flat format, you would use a function like readxl. From that, the file extension there is either .xls or .xlsx. And the latter of those is the newer of the two. Excel files, you may not be familiar with them. They can actually hold several different data tables. Think about several different data frames in the same file, and they're referred to as sheets, okay? And sheets can be numbered or they can be named. So you can pull those in just by saying a sheet specification, and then there's also some kind of column specifications that you can use with readxl as well. Haven, by contrast, is used for data that comes from SAS, SPSS, or Stata. And the function names are exactly what you would expect. Read_SAS for SAS files. You can see the file extension there, SAS7bdat. Those are SAS files. SPSS or .sav files. And then for Stata, DTA files. So that's readr. It goes over a huge array of importing flat data formats into R. It doesn't cover the cases of web formats or databases, but we'll cover that at a different time.